Hello everyone. Today we are going to start with central limit theorem. Over here we are going to look at the following. First of all, we are going to do some recap of the terminology we have learned earlier. Then we're going to look at sampling, distribution of sample means. And then the main thing which we're going to talk about is the central limit theorem. Our main focus is going to be on the sample means. So let's do some recap. The first thing we're going to talk about is the definition of statistics. Statistics is the numerical summary of sample data. For example, the proportion of left-handed people in a sample of 200 people, or the average score of, say, my students of around 30 people in a class. We would look like the average scores of them. Or I would like to look at the standard deviation of the 30 students of my class. The next definition we will look at is parameters. Parameter is the numerical summary of population. For example, the proportion of left-handed people in New York City. In practice, what happens is we seldom know these parameter values. So what we normally do, we look at sample statistics. That is the statistics we get from the sample data. And we use this sample statistics like sample mean, sample proportions to make predictions about the population. Now, the first thing is when we take a sample data, our always sample data is from a simple random sample. Very important. The sample data we are looking at is the one taken from a simple random sample. Now what happens? This sample statistics is a random variable as a result. Now if you recall, what is a random variable? Random variable is a quantitative variable whose outcome depends upon chance. So the sample statistics, which is a random variable, that means it is a quantitative variable whose outcome is going to depend upon a chance, and as a result, these random variables will have a probability distribution. And hence, the sample statistics, which is a random variable, will have a probability distribution. The definition we say is the probability distribution of a sample statistics is now going to be called a sample distribution. So once again, the probability distribution of a sample statistics is called a sample distribution. Now let's go ahead and look at the central limit theorem for sample means. Okay, so this is what we're going to look at, the central limit theorem for sample means. Now sample mean is basically the averages. Before I go deeper into the central limit theorem for sample means, I'm going to do some little concepts over here. So let's look at this one. Now remember, what we are doing is we are trying to estimate a population mean, which we always denote by mu if you remember, with the sample mean. Now sample mean, if you guys remember, is x bar. For example, I have this huge, big population. Do you see that over here? I think the circle is much more nicer than what I'm kind of making around. So what is happening? So we have a bunch of data sets over here. Now this is a big, huge population. Now, it's impossible for me to look at every data set or data element in this population. So if I want to make an inference about it, it's much more easy to go and pick some little samples from it. Suppose I pick this sample, say A. Or I pick somebody goes and picks up this sample, say call it B. Now we can easily find the sample with this mean for this set A, or we can find sample with mean x bar for this B. Or somebody else might go and pick up, so they like this bunch of data sets, so they like this data set. And say this is C. They like to find the sample mean for this. So depending upon what data you are picking up from this big, huge population, you are going to make inferences based on the sample from statistics from that data set. So the actual value of the sample mean depends on which sample is chosen. Very, very important. Somebody says they pick up A. So they might have a sample, say, X bar A. Or somebody picks up B. They will have a sample mean would be X bar B. Somebody goes and picks up, say, this set. And we say call it D. So they will look at the sample mean for this set, say X bar D. So what we see is the sample mean is a random variable because randomly we are picking up data and from the whole population as we pick up random mean. So this sample mean, and this is what we denote by the capital X bar. That means it is from the whole population data set, we pick up a sample and then we find the mean of it. So this sample mean clearly is a random variable because of the way how the data is picked up. And hence what is going to happen? This will have a distribution, or we call it a probability distribution. To make life simple, I will say it is sample mean is a random variable. It has a distribution. In the back of our mind, it has a probability distribution. Now, the distribution of the sample mean will tell how well we can use the sample mean to approximate the mu. Mu, guys, remember, is the population mean. Very important. Whenever you see the notation mu, it is used only for population mean in our statistics class. So once again, so if I know the distribution of the sample mean, okay, so if I know the distribution of the sample mean, this will help us to recognize how well the sample mean can be used in approximation of the population mean. So I'm going to start with an example to show how we can find this distribution and what is it going to help us with. Okay, so I'm going to start with a very simple example here. So the first thing we're going to talk about is population distribution. This is the probability distribution of the population data. Okay, so what I'm going to say is, suppose I have a small population of 5 students, and these 5 students recently gave their midterm in a statistics class, and these were the scores. The scores are 70, 78, 280s, and a 95. Now this is the whole population, only 5 students. And we say let X, the capital X, is the midterm score of a randomly chosen student. So we can exactly find the mean of this X, that is the midterm scores. If you plug it in your calculators, you all know, even if you don't plug it, you can simply add and then divide by 5, which will give you 80.6. The standard deviation, definitely use your calculators to the one variable stat. So I will just quickly show you how to do that. Go ahead, click on stats. By default, the edit button is highlighted. Press enter. Then plug in the numbers. The numbers are, if you remember, is 70. Enter. Then we had 78. Then I think we had 280s. And a 95. Yeah, okay. Now what you're going to do is do the one variable stat. Click once again on stat. Use the cursor key to move to calc, and the number 1 is highlighted. Press enter. It says frequency. In the list is L1. Don't worry about the frequency list. Just take your cursor to calculate, and then press enter. No, normally, do you see what is the sample mean here? 80.6. And this is the population, guys. So the population is this one, sigma, is the population standard deviation. It is 8.089 or 8.9. Okay, and that's how we calculate. And this is what we have the answer. Now keep in mind, our whole population is just these 5 students. Now remember, our idea is if I take samples of this standard population, if I look at these samples, what would be its distribution? Because we want to look at the sample means of them, okay? So let's go ahead and work further into it. Now, we're going to look at the sampling distribution of the sample mean. Okay, so what you're going to do is, this is the, remember, it is the probability distribution of the sample mean, and we denote it by capital X bar. What it does, it lists the various values that the sample mean can assume and the probability of each value of the sample mean. So once again, going back to this the problem we started with, we say for a small population of 5 students, we would consider all possible samples of 3 scores. We can also calculate all possible samples of 2 scores or 1 score or 5 scores or 4 scores. I'm just going to look at all possible samples of 3 scores. We'll first try to figure this one out and then see what the rest goes. And it can be selected without replacement from this population. Now let X bar, that is the capital X bar, the sample mean, denote the sample mean of size 3. In other words, when we're going to look at samples, it's very important to know the size of the data set we are looking at. So what we are doing here is, we have a whole population of 5 students, and now we're going to pick up a sample size of 3 scores of these 5 students. And we would look at all possible samples, and we're going to look at their sample means. So the first thing is, what are the possible outcomes? And then what are the average scores for all of these possible outcomes? And what are their probabilities? And after that, we will find the mean of the random average score. Okay? Remember what we're doing is, we are looking at the sampling distribution of the sample mean. Okay? So the bigger picture, once again, and let me tell you, is that we have a whole population is 5 students, and I'm randomly pick samples of scores of these 5 students. Okay, I'm looking at the midterm statistics score. Randomly go and pick up scores of 3 of these students, and I look at all possible samples. Then I go and look at the sample mean of individual of these 3 scores. And then we would go further with it. So the first thing is that what are the possible outcomes? Okay, so let's go and delve further into it. Here is the answer. Now, for a small population of n equals 5 who recently gave their midterm, let us consider all possible samples of 3 scores. So we look at all possible samples. So the first thing is, what are these possible outcomes I can have? Okay, remember we have 5 of these scores. So first thing we're going to do is, we're going to make our life simpler, okay? Because we have letter grades, not letter grades, number grades, 70, 78, 80, 80, and 95. So these are the midterm scores for the 5 students. We say, let each of the score be a letter. A is 70, B is 78, C is 80, D is 80, E is 95. So these are all the 5 scores. We have given them a letter grade. Now, we're going to look at all possible samples of these 3 letter grades. In other words, I can have a sample of A, B, C. In other words, I can gather, say, scores of 70, 78, and 80. Somebody says, no, I like to have the scores of, say, the student, the letter A, B, and D. Oh, fine. What is A? 70, 78, 80. Somebody says, no, I would like to have B, C, and E. I would like to look at the samples of this. Fine. What is B, C, E? B is 78, C is 80, and E is 95. Now we'd like to know all possible samples. So there are 10 possible outcomes. It will be ABC, ABD, ABE, ACD, ACE, ADE, BCD, BCE, BDE, and CDE. So what we're going to do, we have first gathered these sample sizes of 3 of these scores and looked at all possible combinations. So we get 10 of these combinations. Now what we're going to do is we're going to go to each of these scores, okay? Each of these scores, and we're going to find their sample mean or average score. So we're going to find an average score for this one. So this one be this X bar, and this one would be, say, again another X bar for this one. Let me use a different color for this one. So this one will have, say, X bar blue for this one, and say we have BCE, we have another X bar, and suppose for CDE we have another sample mean. So we look at all sample means of all these 10 possible sample scores. Okay. Now we would like to know what are the average scores for each one of them. So in the next slide, you will see the average score for each of these sample scores. Now, so once again, we're looking at the sample mean. The sample mean is the sample mean of size 3. That means what I'm doing is I'm picking up 3 scores. I'm looking at all possible 3 scores. So we had 10 of them. So these are the samples we took. And these were the scores, because remember we were making a life simple. We say scores in the sample. One could be 70, 78, 80, and all these possible. Then what we do is we go and look at the sample mean of each of these samples, or the average scores for each of these samples. So we get 76, 76. Then for A, B, E, or like for 70, 78, 95, we got 81. For 70, 80, 95, we got 81.67. We actually get it 2 times. Then 84.33, 84.33 again 2 times, but the rest they were ones. Okay, what we're going to do now? Now we are going to collect all these average scores. Now what you're going to do is we're going to collect these average scores, because we're looking at these. Because remember, these average scores are as a random variable because of depending upon these random sample data sets we had picked up. So these sample means, you see, this capital sample mean of sample of size 3 is a random variable, because it can become 76, it can become 76, or it can become 81, or 79.33, or 85. So that means this sample mean of sample data of size 3 is a random variable. If it's a random variable, guys, remember, it will have a probability distribution. And if you recall, probability distribution simply means that this sample mean will take some values, and each of these values will have a probability. Okay, so let us look at what are the values the sample mean can take. The sample mean can take 76. Now, how many times does it take 76? 2 times. So what is the probability of this sample mean when it is 76? Total were 10 of them, so it is 2 out of 10, which is 0.2. Now, what was the other value for sample mean? 81. 81 only happens once. So that is 1 over 10. Then we look at 76.67. That's also once this sample mean takes a value for. Again, its probability for this sample value is 1 over 10, 0.1. Similarly, 79.33 is 0.1. Now, 81.67, that is the sample mean of the random sample of size 3, appears twice. So out of these 10, what is the probability of getting 81.67? 2 over 10. Similarly, the same for 84.33. Similarly, the same for 85. Now remember that the sum of all these probabilities is always going to be 1. And when you add this one, it is equal to 1. Okay. Now, so what we have done is we have found the average scores for all possible samples of size 3, and we also found its probability distribution. Now, we would like to find the mean of this random average score. Now to find the mean of the random average score, because the mean of this sample mean, remember the sample mean is a random variable and hence it will have a probability distribution. Because it has a probability distribution, it will have a mean and a sample and standard deviation. So we are looking at the mean of the sample means, okay, or it is the mean of the random average scores. Now the formula, if you remember, it's multiplication because not equal to. So it's mean of the sample mean is the expected value of the sample mean is summation xi times f of xi, that is the frequency of values of each of these sample values, and it is 80.6. Now this is done by hand, but we actually can also do by using our calculators. So now I'm going to show you how to do by calculators. Now, in order to do this by calculators, to find the mean of the sample mean, remember we had these values written. In the previous slide, we had 76, which was 0.2. It appeared twice. And then we had what? We had 76.67. Okay, let me take a nicer space, guys, here. Okay. So we had 76, 76.67, we had 79.33, then we had 81, then we had 81.67, then 84.33, and then 85. Now these were the various values of the sample mean. Okay, and what was the probability of these small values of the sample mean? 0.2, 0.1, 0.1, 0.1, 0.2, 0.2, 0.1. Now I would like to find the mean of this sample mean. I'm going to get my calculator, plug these values. Okay, so in order to plug these values, guys, keep this table in handy. We are going to go and now use the feature of stats. Click on that, edit, press enter. Okay, let me get this here. Okay, now these values, you're going to put L1, the values of the sample mean. So we can take the cursor and L1 and clear, okay, and press enter. Now just let's put in the values we had. We had 76, enter, 76.67, enter, 79.33, enter, 81, enter, 67, 81.67, enter, 84.33, enter, then 85. Okay, then enter. Take your cursor to the second column, L2. Now 76, remember, was 0.2. Enter, then 0.1, enter, 0.1, enter, 0.1, enter, 0.2, enter, 0.2, enter, 0.1. Okay, so we check everything. Yeah, now we're going to go ahead and do stat because you want to find the mean of this. Then take your cursor to calc, do the one variable stat. It's already highlighted, press enter. Now here you are having list L1, that's fine. Now frequency list, remember, it is how many times that number was appearing on L1. So frequency list, take your cursor down. Here we're going to write L2. So do second and 2. So L2 pops up. Okay, then take the cursor to calculate, press enter. Notice what you get. The sample mean is 80.6. Isn't that wonderful? 80.6, which is the same as the population mean, guys. Okay. So what we found when we used our calculators, that the mean of the sample mean is exactly the same. This is exactly the same, guys, as the population mean. Okay, so now remember, our sample mean has a probability distribution. That means it will also have a standard deviation. So now we would like to find the standard deviation of the sample mean. In other words, we would like to find sigma x bar. Now there's a lot of work on it. What really I want to focus here is to show you for different sample sizes, what is the standard deviation of this sample means. When you have n to be 1, notice when n is 1, or the sample size is 1, or the sample size is 2, 3, 4, 5, the mean for each one of these simple sample sizes is the same as the population mean, 80.6. Whereas, when you look at the standard deviation, now remember what's the meaning of standard deviation? It is the variability of the data set. If you are having samples of size 1, that means you only have, what does that mean? You only have samples of size, that means either it is 76 or 76 point, samples of size 1. You go back to the original sample, that's it. So samples of size 1, and you're looking at the means of the sample means. So if it is sample of size 1, it's basically going to be what? It's going to be 70, 78, 80, 80, 95. Look how dispersed they are. Because what is the sample of 70? Just 70 itself. Sample of 78, 78, and stuff like that. Now, if you're having of sample means of size 2, in other words, we will have combinations of 70 and 78. We will have combination of 70 and 80. Now this is these two, or this can be first and the fourth, 70 and 80, 70 and 95, all possible samples, and we look at the means of each one of them, and that's how the means come out. So these are how they are dispersed around the sample mean. Now they are much more closer as compared when the size was 1. Let's look at size was 3. When size was 3, remember what was the sample mean of each of these samples size of 3. So if you had 3 of them, so remember 76, how did 76 come about? 76 was, for this one we had 70, we had 78 and 80. And then we had again, then we also had 70, 78, 80. Then we suppose, we had 76.67. So for this one, we had 70, then we had 80 and 80. This was scored C and C. Okay, this was A, C, D. This was A, B, C sample. So these are the various samples. So notice when I took the sample size to be 3, what happened? The deviation or the variation in the data set of the sample means of the sample size 3 is much more closer to the population mean as compared to the sample size 2. Now when we took samples of size 4, they actually became more clustered together towards the sample mean. When it was 5, the sample mean is the same as there is no variation. So notice what happens is as the sample sizes increase, the standard deviation of those sample means of various sample sizes, they actually are different, but they get more and more closer towards the sample mean when the sample size is large. So here is the most important slide at this point for us, and that is, what is the observation we learned from this example? It says when we are drawing samples from a population, the mean of the sample mean will always equal the population mean. This mu, guys, is the population mean. And whenever you see a symbol of mu with subscript x bar, that means we are talking of mean of the sample mean. The standard deviation of the sample mean is given by sigma, which is the population mean. Remember, sigma on its own with no subscripts is the population mean. And we divide this by the square root of the sample size. This gives the standard deviation of the sample means. And there's a lot of algebra, as he said. I just showed you how the graphical image looks like in the previous slide. Now, there's a terminology, guys, very important terminology. And that is that the standard deviation of the sample mean is called the standard error. And the reason the standard error comes up is because we are trying to estimate the population by a sample data set. And that's where the errors are going to come. So it's very, very important when you're looking at when you're talking about sampling errors or standard errors, that's basically it is because of you're estimating a population mean by the sample mean. So that is why the standard deviation of the sample mean is sometimes called the standard error or the sampling error, whatever you want to say. Okay, but these two guys, these two formulas are very, very important for us. Okay, now if the size, notice what happens, as the sample size grew larger, the standard error or the standard deviation of the sample mean was coming closer and closer to the population mean. In other words, look at this picture. As the sample size increases, notice what is happening to the standard deviation. It's coming closer and closer to the sample mean. There is less variation. Remember, standard deviation means the variation of the data set. Here, the variation of the data set is basically variation of the sample means. So the sample means are actually clustering more around the sample, the mean of the sample mean. Very, very important. Okay. So what basically remember is, if the larger the sample size, the smaller the standard deviation of the sample mean. Okay. Once again, the mean of the sample mean is the same as the population mean, and the standard deviation of the sample mean is given by the population mean divided by square root of the sample size. Larger the sample size, smaller the standard deviation of the sample mean. They go in inverse. Smaller the sample size, larger the standard deviation of the sample mean. Keep these facts important. So this is, you can say this is a very important slide, guys. Keep this in mind. So let me say this is an important slide. Okay, so the observations which I just talked about, notice that the sample mean, the mean of the sample mean, sorry, when you see this term mu with the subscript x bar, this is called the mean of the sample mean. This mean of the sample mean remains the same, and it is the same as the population mean regardless of the sample size. Whereas the standard deviation will decrease as the sample size increase. And that's where the law of large numbers comes in play. The law of large numbers says that as the sample size increase, the difference between the population mean and the sample mean approaches zero. So we've done a lot of theory. Now it's time to do some examples. Here's the example. It says, according to recent current population reports, the population distribution of number of years of education for self-employed individuals has a mean of 13.6 and a standard deviation of 3. Now remember, this is the information about the population of a numbers of years of education for self-employed individuals. So first of all, we like to identify the random variable whose population distribution is described here. The answer, the random variable X refers to the years of education of self-employed US individuals. Okay. Now, the second question, what is the mean and standard deviation of the sampling distribution of the sample mean for a random sample of size 100? Remember, when you see the word sampling distribution of sample mean, this capital X with the bar or X with the bar means you're talking of sample mean, and the moment you see the word sampling distribution in front of that, that means we're talking of sampling distribution of sample mean. So we would like to find the mean and the standard deviation. Now what we have learned just previously in the previous slide, that the mean of the sample mean is the same as the population mean. And this is the population mean given to us to be 13.6. Now how do we find the standard deviation of the sample mean? The formula is the population mean divided by square root of n. Now the population mean is given to be 3. So 3 over square root of the sample size 100 gives us 0.3. Okay, now this was the mean and standard deviation for a random sample of size 100. Now suppose I increase the size to 400. What is going to be the effect? Let's have a look at that. So in this question says, find the mean and the standard deviation of the sampling distribution of the sample mean for a random sample of size 400. Now the answer is the mean is exactly the same as the population mean. So you don't even have to worry. Just go and look at the population mean. But the standard deviation is sigma over square root of n. Sigma is 3 over square root 400. 0.515. So what is happening? When it was 100, the standard deviation was what? 0.3. But the moment it became 400 sample size, there has a drastic decrease in the sample standard deviation. Whereas the mean remained the same. But the standard deviation decreases as we increase that number of samples. So that's what the question is asking. Describe the effect of increasing the sample size from n equals 100 to n equals 400. So what we notice is from the previous and this slide that when we increase the sample size, the sample mean for both the sizes 100 and 400 remains the same, whereas the standard deviation decreases. And that leads us to the main topic here, which is called the central limit theorem for means. And it says, as n increases, now this n, guys, is the, remember, sample size. Okay, as n increases, the random sample mean x bar that's given by behaves more and more like a normal random variable with mean mu and standard deviation sigma over square root n. So remember two things here. As your sample size increase, the random sample mean behaves more like a normal random variable. And when we talk of a normal random variable, remember it is described by two parameters, by the mean and the standard deviation, which we have already found out from the previous slides. So this basically is the central limit theorem for, I forgot this is sample means. Okay, Now, some facts about the central limit theorem. The amazing thing about the central limit theorem is when you're sampling from any population distribution, now it can be discrete or continuous with a finite standard deviation, that this is going to be true no matter what kind of population you're getting from. Also, it is one of the most famous and important results in all of mathematics, and it helps to form the basis for many statistical tests. So once again, the central limit theorem for the sample mean says if you increase the size of the samples, the random sample mean behaves more and more like a normal random variable, which has the two parameters given by mean, mu, and the standard deviation sigma over square root n. Thank you.